Hello and welcome everyone on my presentation in which we're going to dive through the most recent advances of application of large language models and their evaluation on understanding medical concepts and the textual narratives from the medical image series. My name is Nicolay and I am a research fellow at the Bournemouth University, who is in particular working on the marking medical images with the application of natural language processing techniques. And this is the outline of the presentation that I decided to organize in the three folds. So at first, we're going to cover the nature of medical imaging, in which we tend to answer the necessity of variety of medical images series in the radiology for the doctors and the vice practitioners, the contribution that the natural language processing that could be made for understanding medical images in greater detail. We dive through the atomic concepts that are applying for the imaging through the schema of the fundamental concepts. And we're going to use these atomic concepts in our evaluation of language models. In particular, we're going to experiment on assessing their capabilities, retrieving the related aspects from the textual narratives. Alongside with it, we're going to cover on how confident the existed systems and find out the related applications in the downstream apps. Without all further ado, let's start with the introduction to the medical imaging. In particular, we're dealing with a patient. In several conditions, we wish to look from the inside in a particular body parts and doing the related examinations. For such cases, and nowadays, if we wish to do so, we are running into the several common methods. So these methods are MRI, computer tomography, or ultrasound. And it doesn't specifically matter with which method we're going to go, because all of them, they have their own pros and cons. But the key idea remains the same, is that the output out of these methods represents a signal. So signal is not the endpoint where the practitioners or doctors are expected to see in order to analyze patient conditions. So that is why it is supposed to be weighted or imaged. And this is where it becomes the point of certain challenges and starts the surveillance. So the practitioners or doctors are expected to have a various image series in order to see at the patient from the different perspectives, and at the same time be sure about the diagnosis that they are made about it. And the crucial point here is that not all of the information that is used for the various images comes from the equipment from which we're obtaining the signal and performing the imaging. It is worth to note that the doctor also aware of certain conditions about the patient. So that's why we also have a so-called textual narratives, or the information that is written by a doctor alongside and for the particular image series. So let me give you the quick example. Among all the various data providers, so there is one which is called the Cancer Imaging Archive. This represents a platform, and in general is a provider of various resources about the different parts of the body used for the research. So one collection in particular may represent a series of images, as you can see on the slide, which is accompanied by the metadata. And this metadata usually might be represented in a variety of formats. So one of them is a DICOM metadata, and another is a form of the spreadsheet that collects the necessary fields out of the DICOM metadata. In both cases, we might have the study description and series description as illustrated on the slide in a format, as you can see, that represents just a bunch of the symbols. But for the practitioner or the doctor, it could be valuable information that showcase the concepts that are behind the related image series. And this is where the NLP starts with its contribution to the medical domain. With this slide, I decided to go in general to answer the question on what are the specific fields where NLP actually contributes in the medical domain. To answer this question, I decided to take a look from the different focuses from the perspective of the subject of the studies. So if we don't have a specific subject, we treat it as the general studies. We have similar directions as illustrated in the slide, and it refers to inference with the generative AI models, chatbot assistants, investigation of the medical reasoning techniques. Another area is where the patient represents a subject of the studies, which involves the identification patient-related information, CPG matching with the patient conditions, diagnosing patient conditions, and so on and so forth. However, the way we see the importance behind this analyzing of textual narratives is for the studies that are based on the doctor. So with all of that, we're not claiming to make a huge advancements with the related reports, rather than to see it as a milestones that would lead to the more general task as medical report assessment. Okay, let's then move to the second part of the presentation, where I am focused on understanding atomic concepts that are behind the medical image series. It in general depends on from which domain you're starting the investigation in the related field. In my particular case, I started with this a year ago, and my initial domain and the whole studies were narrowed to the specific case, where I mostly started being focused on the examination of the liver body part. With all of that, the statistic that I have here is represent the view in this particular field, but it generally could be applied for the other body parts. So with all of that, the main visualization concepts that I came to are as follows. So the first of all is the acquisition, is the orientation or direction in which we are performing scans of the body. The second one is the injection or presence of the contrast. So basically, it means that if we have a constant substance that has been injected in the body, then depending on the time we're performing the related exam or analysis, it would affect on the different imaging. And finally is the way how we visualize the signal accompanied with the fact that contrast substance being injected. So as you can see, we have the whole structure that leads us to the various ways of how the result image series we may have. And in order to establish connection between these three main concepts that you can see on the left side of the slide with the facts that could be extracted from the image series on the right side, there is a so-called complex hierarchy of the intermediate concepts that are connected to each other, in which I highlight a so-called atomic concepts. So those concepts that are no longer could be break into the small parts. So this diagram shows the importance that among all of the facts that we can find in the reports, only several of them are meaningful for the particular cases. And then let's move on to the part where we're starting to organize in the related experiments. And in order to do so, of course, at first, we have to decide with which data we're going to go. Again, within this presentation, and my focus in particular is the liver body part with one of the common type of the cancer, dubbed as the hepatocellular carcinoma disease. So in order to start with this, at the first step, we analyze the existed surveys that represent the overview of publicly available resources applicable for the AI-related research. So it's a huge credits to the authors who made already a huge job by analyzing the vast amount of resources that are publicly available. However, when I did this, I realized the huge gap and the absence in the related reviews is that the related studies didn't come through all the related details about the resources. And that becomes the reason of the diagram you can see on the slide, which provides you the common structure of the collections that you may have and that describe the volumetric data of the patient. For those who are not aware of, there are two main concepts on how volumetric data could be presented to describe the patient conditions. So one of them is the DICOM format images. These are usually accompanied with metadata. And another one is NAI standard that is used to collect the whole series of images within one file. It is worth to note that among the main concepts of the collection structuring that involves patient series and studies, usually for series and studies, we have the related narratives. And the rest of the information is usually accompanying all of this, and the presence of this information may vary from one collection to the other. So with this structure, we go further and took the structure lever resources that are relevant for our studies and analyze their contents. By doing so, we found the two major key takeaways. So first of all, there are two different type of resources with which you can deal with and apply in AI. So these are cancer target-oriented resources on the top part, and routine lever resources protocols, which is in the bottom part of the table. It is worth to note here is that the routine lever protocols are not suitable for this type of task is just because they're mainly focused on only one image series, so that it's likely in this collections you might not expect a connection with the patient. And this is the important takeaway, is because if you wish to deal with the medical assistant app that can understand patient and virus conditions, this is likely not a source of resources that you wish to consider. So all of that implies the second takeaway is that we only focused on the cancer targeted oriented resources and use the content out of it in order to construct the dataset of the structured textual narratives. So how we approach to this point, this is what brings me to initial part of our experimental setup. We adopt the pattern matching rules in order to annotate the atomic aspects into the related image series narratives. So in particular, these atomic aspects are illustrated in the slide. There are 6 of them that are part of the imaging, contrast, and acquisition group that we've seen before. And in the bottom part, we illustrate the classes which are supposed to be predicted by models. And this is how, in general, we go with related classification. So using the resources that describes the patient from the Cancer Imaging Archive platform, we compose the related resource with the statistic illustrated in the bottom row of the table presented on the slide. Now let's move on to the methodology that stays a part of our approach in which we are performing the related experiments. So on the left-hand side, we have textual narratives. We also have an input image acquisition ontology that we overviewed before. And within the further 3 steps, we aimed at structuring image series narratives in the form of the following actions. So first action is that we are asking the question towards the large language models or generative AI framework on the diagram in order to obtain the answers for our atomic concepts. And on the third step, we use this information all together in order to have the structured representation. Here, it is worth to say that at the moment, we limit our approach to the particular ontology like the one we overview, but in general, we think of it could be expert system that can automatically break down these concepts and form them into the related questions. Let's dive into more details about the step 1 and 2 in the form of the following textual descriptions that we have for our input information in the model. Conceptually, we follow a so-called like a baseline approach for constructing the related systems. And with that, we're exploiting the prompt-based techniques by forming the instruction that represents a context combined of studies description and series description, wrapped into so-called closed-end question. So the closed-end question denotes that we are directly asking for choosing one of the particular set of the classes. So with all of that, we treat our approach as the so-called text classification problem but with the application of generative AI models. And as for the implementation, we adopt our manually developed no-string framework aimed at applying the various schemas with the universe interface of adapting various models through implementing their adapters. And this framework is publicly available, which is open for free to use. But the key concept here is that we just stick with the one schema and experimenting with the various models by writing the adapters for them. And this is the point where we actually coming to the model setup in our system. So I decided to explain it in the three main components. So by first mentioning the models that we use, the models that were actually evaluated, and how we cope with the measuring the consistency of the models. Among the leaderboards that we can refer to in order to get the best models, we actually here citing the Open Medical LLM leaderboard by Hugging Face platform, from which, while analyzing the top submissions, we found that among two categories of open transparency models and closed transparency models, most of the approaches follow the solutions based on the Llama 3 architecture. Here, as you can see, that various labs has their own approach to fine-tune the proper models suitable for the medical domain. And at the same time, speaking about the closed transparency, we decided to pick up the ChatGPT-4 as the model that showcased the relatively promising results. And speaking about the consistency, to measure on how well these models withstand in the different conditions, we experiment by changing the temperature parameters so that we make sure the models give the similar results irrespective of the setup conditions. This finally brings me to the results that are showcased in the related table. We use the F1 measure to cover precision and recall parameters among the classes for each atomic aspect in particular. And among all of these models, I decided to group them into three categories. So the first one of the high-performing models is the category that combines the closed transparency models, including the open transparency one, which is Llama 3 70 billion parameters. The second category is the model that's with the scale of 8 billion parameters. And the last one involves the small language models of 1 billion and 3 billion parameters. So let's have a look in a more accessible way on what we got out of this table. So we have the following findings that I'm going to illustrate within this slide, and they are twofold. First of all, the open transparent Llama 70B performs similar to the ChatGPT systems, and here's why I can recommend to use it out of the box for the latest structuring. And the second noticeable fact is that such as small language models, those ones that are at scale of 3 billion parameters and less, has a drastic underperformance comparing with the other models. And most importantly, they are actually lost confidence in their responses, where you can see the variations among the several runs on these diagrams. Now let's take a look on why specifically this is happening by analyzing the results in depth. So these diagrams at the moment shows the results for the high performing models or large scale language models. And on the next slide, it turns to the small language models. However, I would like to quickly slide back and forth so you can visually see the noticeable difference on what's going on there. So by analyzing what's going on with the small language models, for each category in particular, it is possible to see that it is mostly predicted one or two classes, and it can't go even further. For example, for the weighting technique, we can see that mostly models cannot understand the difference between T1 and T2 series. As for the contrast timing, it turns out that most of the models predict the portal timing of the contrast injection, And similar fact comes to the other aspects, such as technique and plane, where models tend to predict only one class. So that means they don't differentiate the various setups mentioned in the textual narratives. If we're taking a look on what's going on for the cases where large language models answer with related explanations, is the point where you can notice the hallucination effects. So here's an example of the case with the 3 billion parameter models answered for the fat suppression. It is worth to see that on the one hand, it starts by understanding the fact that the text mentioned the fat suppression, such as FS, but at the same time, it starts to decline from the original decision by mentioning it is not explicitly mentioned as the sequence type. Another example with the timing, and this case happens with actually relatively large scale model, such as LM3 70 billion parameters. And this case is way more tricky. It actually shows that those interdependencies between atomic aspects that we investigate earlier is quite hard to catch with the models in such a default setup. So this case shows that, for example, model understand the fact that there is a timing in the textual narrative, but at the same time, it doesn't implies the presence of the contrast, which is sort of contradictive, considering our initial observations and the way the dataset is constructed. With all of that, this brings me to the downstream applications, where we can see how these techniques that we overview together can be applied in the real case scenario. So, and this is going to be a two-case example. So first example is the analysis of the inner content of the dataset. This illustrates the so-called demo, where for each patient, instead of mentioning the content in such narratives, we provide the structured information of the grouped content alongside with the amount of the related image series. And the second example is when we're coming towards the assessing the reports made by novice practitioners or doctors with respect to the goal truth information. And this is the sweet spot where the generative AI can contribute with explainable AI for highlighting differences between the ground truth data and submitted reports. And most important key takeaway here is that we can use these atomic concepts in order to enhance the related explanations and make it more solid, comparing with those approaches that didn't go with the related key concepts. And finally, let me conclude on what we overview within this presentation. The conclusion is going to be a threefold. So first of all, we all view together the concepts of the medical images, its importance, and how specifically NLP can contribute in this area. Secondly, in outcome of the experiments, we found together that the results really depends on the scale of the models, and that there is a significant drop in the performance when you're dealing with the large language models. So my recommendation over here is not to spend the time to fine-tune the small large language models, but instead go with the solutions out of the box, sized by 8 billion parameters and more. And finally, as for the downstream application, we overview how these concepts of the atomic concept extraction could be used for assessing content of the medical resources. And the second one is how this could be used for analyzing medical reports. And with all of that, that was me. Thank you very much. And I'm happy to answer your questions by reaching you out on the other social media systems.